Okay, so welcome to Math389 Advanced Analysis. This is lecture 9. And what I want to do today is I want to talk about differentiating series, and I want to talk about statistics. And by statistics, I don't mean the half of the department that's leaving. I want to talk about just finding good things to study. And how do you find what's worth studying? What questions do you ask? And I think this would make a really nice math outreach article. Okay, so the first is differentiating the geometric series. This is probably the easiest infinite series to justify differentiating term by term. Now, normally you might differentiate e to the x term by term, and you see that the derivative of e to the x is e to the x, but you have to justify why is the derivative of the infinite sum of the derivatives. And this is where hopefully you've had a good analysis class, and in that good analysis class, they've talked about radius of convergence of series, and if you converge absolutely, you can differentiate within that. So that's a big theorem to use. Let's try to do this without using any big theorems. So let's say f of x is let's do g of x because it's the geometric series. Let's say g of x is 1 plus x squared plus dot, 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 dot. I'm going to write this as g of x is 1 plus x plus dot, 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 plus x to the n, plus x to the n plus 1, plus x to the n plus 2, plus dot, dot, dot. What can you tell me about the tail? So what can you tell me about the x to the n plus 1, plus x to the n plus 2, etc.?
Geometric series scaled by x to the n plus
excellent. It's just x to the n plus 1 times 1 plus x squared. It's just a geometric series. So the geometric series is I can do a finite approximation by just taking the terms up to x to the n, and then I'll have x to the n plus 1 times g of x. So what can we do now? I can think of two things to do. I'm sorry?
Group by terms and solve.
So what do you mean by group by terms? Good. So I could say one possibility is this is just 1 minus x to the n plus 1 times g of x is 1 plus x plus dot, 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 plus x to the n. So g of x is 1 plus x plus dot, 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 plus x to the n over 1 minus x to the n plus 1. And then I can differentiate term by term. I can use the quotient rule here, right? So that's one possibility, is to now use the quotient rule. Is there anybody eager to use the quotient rule? Okay, but it's possible. So I'll leave that as an exercise to use the quotient rule. But this is an upper level class. You guys have a vote and your vote counts, so we won't do that. So the other possibility is g prime of x is 0 plus 1 plus 2x plus dot, 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 plus nx to the n minus 1 plus, and now what rule do I use? I use the product rule. N plus 1 x to the n g of x plus x to the n plus 1 g prime of x. Why am I allowed to do this? So what rule am I using here? Product rule, and what else? and finite sum. So both of those are fine. Now, I am implicitly assuming that g of x is differentiable. Is g of x differentiable? Does g prime of x exist? Why? So why does g prime of x exist?
Because it's a sum of differentiable terms.
But it's an infinite sum. What does g of x equal? You all know what g of x equals. Or you should all know what g of x equals. G of x is 1 plus x squared plus x cubed. What does g of x equal? 1 over 1 minus x. If the absolute value of x is less than 1. So g prime of x clearly exists. It's just, how can I write g prime of x? But we know g of x exists. What is g prime of x? I'll get a negative will be in first. It's just going to be 1 over 1 minus x quantity squared, or 1 minus x to the negative 2. So now, putting all the pieces together, we get g prime of x is 0 plus 1 plus 2x plus 3x squared plus dot 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 plus n x to the n minus 1 plus, now g of x is 1 over 1 minus x, g prime of x is 1 over 1 minus x squared, so I'm going to get n plus 1 x to the n 1 minus x plus x to the n plus 1 over 1 minus x squared, if I've done everything correctly. I'm just substituting in for g of x and g prime of x. And for the first piece, I only have a 1 minus x in the denominator. The second piece is a 1 minus x squared. So I've just multiplied the first piece by 1 minus x over 1 minus x. So they have a common denominator. If I take the limit as n goes to infinity, what happens to this piece as n goes to infinity? If the absolute value of x is less than 1, what happens to this piece? Goes to 0. Why does it go to 0? Well, the x to the n plus 1 is no problem. The n plus 1 times x to the n is a little bit of a problem, but x to the n is going to go to 0 a lot faster than n is going to go to infinity. If you had to prove this rigorously, you could do L'Hopital's rule. You could probably do maybe ratio test, Rooch test. Probably ratio test would work nicely. And so this will tell us that as n goes to infinity, g prime of x is going to go to the infinite sum. So this allows us to prove that the derivative of the infinite sum is the infinite sum of the derivatives. In this special case, we are not using anything about radius of convergence, that you can differentiate freely within that. How many of you actually saw that theorem in one of your analysis classes?
Which theorem?
That if you have a series that converges absolutely, you can differentiate within inside the radius of convergence.
No, I only saw if the series converges absolutely.
Yeah, we did not cover derivatives.
Yeah, we didn't get rearrange the
We did not
terms.
take derivatives.
Well, like the rearrange the terms.
Yeah.
At least the four of us.
Yeah.
All right, so the technical malfunction has been fixed, which is excellent. And so I'll stop this here just to be absolutely safe, that to make sure that I'm going back. So the reason things worked so nicely is that the tail of a geometric series is a geometric series. And because of that, we have this wonderful way to reduce the tail to a fixed formula, and now it's a finite sum. And because it's a finite sum, the derivative of a finite sum is the finite sum of the derivatives. That is not so bad to prove. And what we can really use is, if I give you, f1 plus f2 plus fn, and we want to take the derivative, Well, by induction, it's F1 plus Fn minus 1 plus Fn. And now we have a derivative of two things. And because it's a derivative of two things, the derivative of a sum of two things you've proven is just the sum of the two derivatives. And now that we have all of this, it somehow went all the way up there. Now that we have all of this, then we can just keep going by induction. And so if we just continue, eventually we get to the sum of all the derivatives. And so if you have a finite derivative, a finite sum, it's no problem. Okay. Let's look at some fun functions. So here I'm going to consider f of x is the sum, and it goes from 0 to infinity, the sine of 4 to the n x divided by 2 to the n. Or if you want, I can put the 1 over 2 to the n in front. Does this sum converge? I mean, before we even talk about differentiating, we should at first see if the sum converges. Does the sum converge? Yes. And because this is an advanced class, we can also say it's clear it converges and just move our hand in some kind of upward motion that it's trivial that it converges, right? It's really nice to be in an upper level class. Years ago, I was teaching complex analysis, and I was showing an interesting proof technique to a contour integration technique. And I was expecting to only spend about 5 minutes on it because it's a standard calculation. And then I realized, oh no, this is the first time anybody in the class has ever seen this technique. It's not a standard calculation for them. This is when they're meeting it. And so what was supposed to just be a 5-minute became, a 30-minute digression of why can we do this? Why is this going to converge nicely? 2 to the n is big, and sine of 4 to the nx, good. So 1 over 2 to the n goes to 0 fast, and sine of 4 to the nx is less than or equal to 1. So because of that, everything is going to be fine. If we wanted to estimate the tail, we can bound the tail by a geometric series. So we can bound the tail with no problem. The sum n goes from 0 to n of 1 over 2 to the n sine 4 to the nx plus the sum n goes from n plus 1 to infinity, 1 over 2 to the n sine of 4nx. How big is this? This is clearly going to be less than or equal to 1 over 2 to the n plus 1. The sum, let's say m equals 0 to infinity, 1 over 2 to the m. How much is that sum? The sum I think should just be 2. It's 1 plus a half plus a fourth plus an eighth. So this sum over here is just 1 over 2 to the big N. So you give me any epsilon, clearly the sum is going to be fine, right? What's the derivative? So what do you think the derivative of the infinite sum is?
It probably doesn't converge.
Probably doesn't converge, right? Given that I'm spending time on this. What would you like to do? Yeah, we'd love to differentiate term by term. And so the hope is f prime of x would be the sum and goes from 0 to infinity, 1 over 2 to the n. What's the derivative of sine of 4nx, 4 to the nx? Cosine of 4nx. So this is the sum and goes from 0 to infinity of 2 to the n cosine 4nx. And I'm being very, very kind today. Anybody want to give me a value of x?
0.
0. So at x equals 0, we get the sum of 2 to the n, and it goes from 0 to infinity, which is infinity. Right. So I've deliberately chosen an example where it's clear that it's not differentiable at this point. Or maybe it's differentiable, But if it's differentiable, its derivative is not the sum of the derivatives. So I can't use this to prove that the function is not differentiable. I can just use this to show that if it is differentiable, its derivative is not the sum of the derivatives. Does anybody know the saying about a cat and a hot stove? A cat that jumps on a hot stove will not jump on a hot stove again, nor will it jump on a cold one. To each experience in life, only draw the lesson from it that you should. So be very careful about pushing things too far. This does not prove that the function is not differentiable. It just proves that if it is differentiable, its derivative is not the sum of the derivatives. Okay, so you have to be very careful. So f might be differentiable, but if so, derivative is not sum of the derivatives. Okay, so just something to be very careful about. This is a fun function. I deliberately chose it so that there was at least one point. What do you think would be true in general? So we did x equals 0. What if we chose another point? What do you think? Do you think x equals 0 is a particularly bad point?
Because we'll still have 2 to the n, and cosine will modify it. It's not that significant.
Yeah, so the cosine is going to be fluctuating. We're going to get some cancellations with the cosines. But because 2 to the n is exploding, I don't expect that the cancellation is going to be enough. You know, if you want a term, if you want a sum to converge, it's really bad if the absolute values of the terms go to infinity. You know, is it possible to have a sum converge? Sure. But you know, you would need some incredible moving down and then moving up, and then you'd be worried about where do you stop. And then eventually at some term, it might come up a little bit. And so when you look at this function, you look at what's going on, there's incredibly high pips at key points. And so if you had to guess, do you think this function is differentiable anywhere?
Maybe x equal to 1. 0.
Ah, but it's 4 to the n x. There's no point of x where all the cosines will be 0. If I had sine of 2 pi times 4 to the n x, but there's no one choice of x that's gonna work. If I had 2 pi, you know, I could take x equals 0.
Wait, Professor Miller.
Oh, sorry, no, sorry, that was wrong. Yes.
Is this one of the Weierstrass functions?
Yeah, and so in fact, if you look at the very next slide, so it changes things a little bit from the iPad and my computer. This is the Weierstrass continuous but nowhere differentiable function.
Oh.
And so this is a slight modification of it. And so Weierstrass was able to construct a function that was continuous and nowhere differentiable. This is a modification of that where this one is nowhere differentiable as long as a is between 1/2 and 1. If a is really small, then it can overcome the factor 2 to the n that comes from the differentiation. So as long as a is less than 1, you're going to have decay and the sum will converge. But you know, the way to look at this is you're basically getting these little boosts at so many different points, the derivative doesn't exist. This is just terrible that such functions exist. You can have a function that is continuous but nowhere differentiable. Okay. So what I wanted, I've wanted to do this for a while, and I apologize to anybody who's done 331 because you've, I think, seen this before. But oh, I don't know why it has the double tap to edit. That should not be here. There we go. Okay. So I want to talk about the mean. So I assume everybody here knows how to calculate means and averages. Okay. So given two numbers x and y, the mean is the number in between. And the key phrase right here is the. What does it mean by the? Well, we normally use what's called the arithmetic mean. And so you give me two numbers x and y, the arithmetic mean is their sum divided by 2. It turns out there's more than one choice of mean that you can study. So out of curiosity, how many of you have seen other means? Okay, good. Everybody has seen other means before. What properties should a mean have? And without loss of generality, let's assume that the numbers are non-negative. In fact, let's assume the numbers are positive, and we can adjust so that x is not larger than y. So x is at most y. So if you were to create a wish list, what properties would you want?
The mean should be between x and y.
Good. So it would be really bad if the mean between x and y. In one of my favorite nonfiction works, it talks about the British Navy before World War I. And Britain used to have a policy that they could fight the next 2 largest navies in the world. And it got to the point where they could no longer do that. But they were very worried about the German fleet increase. And Parliament thought they needed 4 more dreadnoughts. Churchill thought they needed 6. They compromised. Do you know what they compromised on? 8. Obviously. It's just, as they talked, they realized, whoa, the problem is more severe than we thought. 6 is not enough. That's not the same as a mean. Normally you would think in negotiations, you would end up somewhere between the two. This is a really good property that the mean should have. The mean should be between x and y. And in fact, there's a nice corollary.
Assuming they're not the same, they should be like strictly between.
Well, okay, you could do that, but don't assume that they're not the same. Your corollary would be the mean of x and x is x, right? If I give you the same number twice, the mean should just be that number. Are there any other properties you want on your wish list for means? I'm sometimes a nice person. I'm open to suggestions. What would you like? There's at least one more property that you should have.
Y is less than, or you can see that the mean of x, y is less than.
Okay, so that's a more advanced one. No one's ever said that. If y is less than or equal to z, then the mean of xy is less than or equal to the mean of xz. I like that. No one's ever said that before. I like that. That's a good one. There's a more basic one that you're forgetting because I think it's so obvious.
Want it to depend on both x and y.
No, I mean, it probably will, but there's another property that the mean should have. The mean of x and y should be the same as, yeah, right? So again, sometimes it's hard to remember to make these explicit because it's so obvious, but I probably want my mean to be symmetric. Do you always want that to be the case? Right, so if you're weighting one of the variables, like if you're looking at a class, if I want to calculate the average, well, maybe the final should not count as much as a homework problem. And so whenever I teach classes, all homework problems are always worth 10 points. Not all homework problems are equally difficult. It's just much easier for the graders than coming up with a strange marking for how much should this one be worth. But this is a nice property to have, but maybe we don't require it. So sometimes there are desirable properties, but this eliminates weighted averaging. if say 0 is less than p less than 1/2, we could say the average of x and y, and we'll call it maybe the p average, is px plus 1 minus py. Any other properties you might want? Or do we think that this is a good list of properties and then just try to see what has these properties? Now, the mean of x and y is a number. So there is another property that might be worth having. So I have a list here. The mean should be between x and y. The mean of x and x correlates just x. Symmetric. And then the mean of a times x and a times y should be a times the mean of xy. Does that seem like a reasonable property? This is basically a rescale property. Right? If I'm measuring things in meters or feet, the physical number changes, but the quantity is the same. And so I should just, it's basically saying I have some kind of commutativity. Hey, that might actually justify doing this in this class, right? Operations of order. If I rescale the quantities and then take the mean, that's the same as taking the mean and then rescaling. So now all of a sudden this becomes something that I can justify doing in this course. And it's not just, I like talking about this, right? It's when does order matter? It shouldn't matter which way I do this. Does the arithmetic mean satisfy these properties? Yes. So I've done this with, all the way down to junior high school kids. It's not too bad to show this. There is still an extra property, but I think I'm holding off on that for a little bit. The proof of one, let's just do one just to be definite. We want to show that the mean is between them. So x is going to be less than equal to, I guess it would be equal to, is equal to x plus x over 2, which is less than equal to x plus y over 2, which is less equal to y plus y over 2, which is equal to y. And so it's not that hard to show that the arithmetic mean satisfies those properties. And then we can show all the ones, including the latest stuff that was suggested. I won't go through the rest. The rest are straightforward, including if y is less than equal to z, then the mean of xy is less than equal to the mean of yz. That's a great monotonic property to have. That if I fix x and I vary the second one, as I increase the second one, the mean can't go down. Okay, and so we'll often write AM for the arithmetic mean to just save some space. So is it possible to find another function that has these properties? And if you've seen it before, then that's fine. Any thoughts? So has anybody seen any other means? Okay, what's the mean you've seen? Geometric.
I'm not sure how it's calculated.
Ah,
I don't remember how to do
anybody remember how you calculate the geometric mean?
something.
Square root of something. So you've got all the pieces you need. The square root of something, we've got x and y. Yeah, so geometric mean of x and y would be the square root of x and y. Has anybody ever seen something like this? 1 over x plus 1 over y.
Yeah.
What is this?
Forgotten.
Harmonic mean.
Oh, right.
Do you think that satisfies all the properties?
Yes. Wait.
So all of a
Oh,
sudden
no.
now there's a little bit of algebra that needs to be done, right? It's not as clear looking at this, does this work? What's your first thought when you see an expression like this?
But like the meaning of x and x is not equal to x.
Yeah, so if we take y equals x, and we get 1 over x plus 1 over x is x halves. So how should we modify the definition of the harmonic mean?
Multiply by 2.
Multiply by 2. So if we now put a 2 there, then we get to erase the 2 down here. So could that be a mean? 2 over 1 over x plus 1 over y. Let's just do the lower bound. If I replace y with x, have I made the denominator larger or smaller? I've made the fraction larger, right? Which makes the denominator larger, which makes this thing smaller. So 2 over 1 over x plus 1 over x will be less than equal to the harmonic mean of x and y. So yeah, so it's looking pretty good. If I rescale x and y by a, yes, it's going to rescale the whole thing by a, it's symmetric. So the harmonic mean will work. It didn't work with a factor of 1 in the numerator, but it does work with a factor of 2. And so you can similarly show that the geometric mean is going to satisfy all of the properties. And so I won't go through the algebra. I'll just do a few examples. So if we take the square root of 2 and 8, these numbers were not chosen randomly. I want numbers where I can do nice square roots. You get the square root of 16, which is 4, and that is clearly between 2 and 8. The square root of 1 and 100 is 10, and that's between 1 and 100. So what we're now saying is that the geometric mean of 2 and 8 is 4. What's the arithmetic mean? 5. The geometric mean of 1 and 100 is 10. What's the arithmetic mean? 50.5. Yeah. Do you think the arithmetic mean is always greater than the geometric mean? We've got 2 data points. So sometimes when you're looking at problems, you always want to ask, what's a good way to study? Can I adjust things? Can I rescale? Well, by the last property, the mean of ax, ay is just a times the mean of xy. Without loss of generality, what can I assume about x? So I could try to prove things in general, but without loss of generality, what's true about x? What value can I assume it takes? But or larger than 1, that's a string of values. I want to say I can assume x takes on a specific value. What specific value can I rescale and say x equals? 1. Because x and y are positive numbers. I can rescale and make x equals 1. Or I could rescale and make y equals 1. And that just simplifies the analysis. I could do it in general terms, of course. But it might be easier to make one of the variables 1. So I'm not going to go through in too much detail that this is a function that satisfies all these properties. I'll just do, I guess, one really quickly. X squared is x times x is less than equal to x times y is less than equal to y times y. So x is less than equal to the square root of xy is less than equal to y. Okay, it's not that hard to prove these properties. The harmonic mean was a little bit more work, but not too bad. All right. And then the second, third, and fourth, they're not too bad. And so we call this the geometric mean. We did a couple of calculations, here's a few more. I tried 3 and 12. And every time we seem to be getting that the arithmetic mean is larger. And then you can do lots of calculations. You keep thinking this way, and maybe you conjecture that maybe it's always going to be greater or equal to. So let's try to see if this is reasonable. So one of the things I want you to get out of this class is looking at extreme cases. So the first is by rescaling, has everybody seen the W log? Without loss of generality. Without loss of generality, x equals 1. And then if y is very large, what's the arithmetic mean of 1 plus y? And that's approximately y over 2. And what would the geometric mean of that be if y is very large? In fact, and it's not even an approximation. So we know that if y is large, then the arithmetic mean is clearly going to be. You could, of course, do the other way around. What if we make y equals 1 and we have x become small? In that case, x plus 1 over 2 is approximately 1/2 then. And you can do the argument that way. So again, whenever possible, you want to build intuition. The more parameters you have, the harder it's going to be to build intuition. So by saying without loss of generality, we can assume one of the values is 1. That's much nicer. Now I only have one parameter to vary. Okay, so let's prove it. This is the proof. There's many different ways of proving this. This way uses what many consider the most important inequality in all of mathematics. If x is a real number, x squared is greater than or equal to 0. It's amazing how many things follow from this observation. The square of any real number is non-negative. You just have to figure out what to square. So let's square the square root of x minus the square root of y. And so we get 0 is less than or equal to x minus 2 root xy plus y, with 0 less than x less than or equal to y. So we have 2 square roots of xy is less than or equal to x plus y. It should be screaming at you what to do, right? We don't need machine learning to look at all the different possibilities and try everything, right? Just square root of xy is less than or equal to x plus y over 2. So there's a lot of fun proofs about trying to generalize the geometric mean and the arithmetic mean to more quantities. I'll leave it as this. If people are interested, I'll share some notes on how to push this even further. But wonderful, wonderful result. All right. So now this is something that most of you may not have seen. What if we have 3 objects? And again, the purpose of today is not to prove inequalities, which we are, it's to talk about the thought process of how do you get something. So imagine we have x less than or equal to y less than or equal to z. I might as well normalize them and put them in that order. Does everyone agree that a nice definition of the arithmetic mean is just x plus y plus z over 3? And the geometric mean, just the cube root of their product. Notice that there's a split. The arithmetic mean involves sums of linear terms. The geometric mean involves cubic terms. So is there a mean involving just quadratic terms? By symmetry, they should all have the same coefficient. I'm going to write that coefficient as just something in the denominator. Let's call it a over here. And then I'll raise the whole thing to some power. I'll call that b. So is there a choice of a and b that makes this into a mean? And so it should be at least x. It should be at most z. And the triple mean of xxx should be x. How many of you have seen this mean before? Okay, so I've at least got into something you haven't seen. This is a completely new mean to you then. It's sad that you've never looked at it. right? You've been so focused on the arithmetic mean and the geometric mean. Okay, it's a little sad that you didn't remember exactly what the geometric mean was, but you at least knew it existed. You can Google it if you know it exists. But nobody even knew about this poor mean. What do you think would happen if we had 4 quantities? We'd have another new mean emerge. We would look at all the possible ways of multiplying maybe 4 things to the, I'm sorry, to multiply 3 or 4 things. So can anybody give me any thoughts about what A and B might equal?
Maybe B is 2,
Okay, why is B 2?
because the degree of each term is 2.
Okay. But are there any extreme cases you can look at to try to get a sense of what the answer might be? Can you give me a good, I mean, I've told you, look at the triple mean.
Triple X.
Yeah, triple X. So if we take X equals Y equals Z, then we get the triple mean X, X, X is going to be X squared over A to the B, and that has to equal X for all X. Oh, sorry, it's not X squared. What is it?
3x squared.
3X squared. Oh, there you go. 3x squared over A to the B has to equal X for all X. What are your thoughts for A? What are your thoughts for B?
A is 3.
A is 3, and B is 1/2. So you were close with 2. You said the exponent should be 2.
Oh yeah, I meant 1/2, but yeah.
Right. And then when you do something like that, that gets you the right power. If you think about what's going on, if X and Y and Z are in meters, then you have area, you have meters squared. How can I get a meters from a meter squared? I have to take a square root. So just by looking at unit analysis, it strongly suggests that we want B to be 1/2. And looking at this, it suggests A should be 3. So you can now go through, we now have a candidate, and you can show that this candidate works. And so, this is just, going through the calculation we mentioned, looking at the special case. Okay. And so when everything works, we get B has to be 1/2, A has to be 3. And, if we calculate the triple mean of 3, 4, 5, we get 3.958, which is more than 3. It is less than 5. And you can start comparing the triple mean. Where do you think the triple mean sits? So we have the arithmetic mean of X and Y over here. Well, let's see. The arithmetic mean is the larger one. So maybe we should put the arithmetic mean all the way here on the right. Let's do X, Y, and Z. I didn't prove the arithmetic mean for 3 is larger than the geometric mean for 3, but I'll assume you will trust me on that, or you can prove it yourself. Any guess where the triple mean that we just introduced sits between these two? Yeah, it sits between them, right? So 2 of my friends at the University of Connecticut wrote a really nice paper showing that these means do have exactly this kind of property. You have the geometric mean at one extreme, and they keep getting larger and larger and larger until you get to the arithmetic mean. Does it make sense that the arithmetic mean should be larger, or at least as large as the geometric mean? If you think about what's going on, you're taking square roots. So the square root, because I can always assume my smallest number is 1. The square root is going to really push my numbers down. And so, you have that poor situation where you had 100 on one exam, or 1 on the other exam. Your geometric mean is a 10. That's a failing grade. Whereas your arithmetic mean is a little bit above a 50. So if a 50% was passing, you would pass. So it's worth getting a sense of how extreme things are. Now, if I have four numbers, how do you want me to denote the four numbers? I could do x1, x2, x3, x4. I could do A, B, C, D. I could do W, X, Y, Z. Any preference?
X1 to Xn, probably that's, we're going more than 4 at some point.
At some point. So we can do x1, x2, x3, x4. I have four numbers. I could calculate the mean of the first two. I could calculate the mean of the second two. And so that will give you, I'll call it mean x1, x2, mean x3, x4. What can I do now? I can take the mean of the means. The mean of x1, x2, the mean of x3, x4. What do you think that should equal?
I suppose the overall mean.
Wouldn't it be nice if it's the overall mean?
That's not the same function.
So this is where things get interesting.
Sure.
By abuse of what's the next word? Notation. Have you ever heard that phrase before? My freshman math book talked about vector spaces. It was a wonderful class. We did multivariable calculus, linear algebra, point set topology, vector analysis, all in one unified class. And you would do a little bit of multivariable calculus, and you would do some linear algebra so that you could do multivariable calculus correctly. It was wonderful how they fed on each other. And I still remember it mentioned that if the empty set is considered a vector space, this could cause some issues. Does the vector space have to contain the zero element? Or is the definition, there is some element such that anything added to that element, anything from that space added to that element is itself? Well, there is nothing from the space. So depending on how you want to parse things, can you consider the empty set a vector space? And the book just said, you know what? It can become a little bit problematic. So whenever the empty set being a vector space causes an issue, we'll just exclude it. And we'll trust that you can figure out when it should be excluded. Mathematicians are often very bad about not being explicit about what notation means. What does the absolute value of x mean?
X is a real number, then it is.
So if x is a real number, this is the absolute value of x if x is real. What if x is a vector?
How far it is from the origin?
So distance from origin if it's a vector. And so I often use the notation double lines x with an arrow over it to highlight the fact I've got a vector and I'm taking its length. But a lot of other people say, just write absolute value of x. And it's clear from context what x is. I like to be very explicit. So when we say mean, we could be talking about different means. And so we're talking about the mean of two things compared to the mean of four things. So maybe we should put in subscripts. These are the means with two items. And the means of these with two items should be the same as maybe the mean with four items. Is there any reason why I'm looking at four items and not three items?
You mean on the right side?
Well, both sides. I mean, why am I looking at taking four items and not taking three items? I'm sorry? So I can group them. I can talk about the mean of two items and the mean of two items and the mean of those two means. If I only had one item for the second set, if I had three items, would I expect something like this to hold? Because then I'm considering the two groups to be weighted equally. but one of them has 2 observations and one of them has 1 observation. So sometimes it's easier to look at powers of 2 than to look at 3. So it's not always clear what's the next case to look at. For some things, you just increment by 1, others you increment by powers of 2. So do you think the 2 means of x1, x2, x3, x4 is the same as the 4 mean of x1, x2, x3, x4?
At least for geometry. Yes.
And what else? So is this a property that you would want your mean to have? And notice now that we would have to have several different means, that we would almost have to have a family of means. We would have the arithmetic family and the geometric family. So now we have
Arithmetical.
families of means, right? So is everybody comfortable with having a family of means? And so we'll go to that in 1 second. I guess I had one thought I wanted to do beforehand. If you've taken a class with me, you know I love to highlight the fact that whenever you see a product, you should have a Pavlovian response of take the logarithm. So the arithmetic mean and the geometric mean are actually related. The log of a product is the sum of the logs. So if I take the log of the geometric mean, so the log of the square root of xy, that's the log of x to the 1/2, y to the 1/2. That's 1/2 log x plus 1/2 log y. That's the arithmetic mean of log x log y. So the geometric mean of x and y is actually the same as the arithmetic mean of the log of x and log of y. There's a transformation between the two of them. Now that we know that there's a transformation between the arithmetic mean and the geometric mean, what might you hope for also happens? Yeah, are there other transformations for the other ones? Or is this just, we're really lucky from the extreme case, and in anything other than the extreme case, we don't have? This would be true if I had more than just a product of 2 things or sum of 2 things. This one would generalize nicely. Is there such a relationship with these other means? You know, does this generalize? The hope here is that if I prove something for the arithmetic mean, I get it immediately for the geometric mean. Just take for the arithmetic mean e to the x and e to the y. And then that's the same as the geometric mean with x and y. So the hope is that I don't actually have to come up with separate proofs for the geometric mean and the arithmetic mean, that by this observation, it's enough to study one of them. And then for the other ones, hopefully there's a similar game I can play. I don't know if there is, but maybe there is, and maybe we're lucky. Okay. And so as I mentioned here, this is the last property that we want to do. I used A, B, C, and D because subscripts don't work as nice. I have to hit the underscore, and that's more work for me. So I used A, B, C, D. We'll talk about that in a moment. As I promised, here are some links in case you want to see more about stuff like this. Do you want to do things for the arithmetic mean or the geometric mean? For looking at 4 items. I'll accept one of 3 answers. What's one answer I will accept? Arithmetic mean. What's another answer I'll accept? Geometric mean. And there's one other example answer I will accept. I won't accept neither. Close to neither. Differs by 1 letter. Either. Because they're the same. Right? By a transformation, it doesn't matter. Which would you rather do? Work with the sum or work with the product? Sum, right? They're equivalent. The log of a product is the sum of the logs, but we're just trained. How many of you have done Riemann products? No one. How many of you have done Riemann sums? Everyone, right? We are just more used to adding things than multiplying things. Which would you rather do, product or sum? Probably the sum, right? So let's look at the sum. So we want the arithmetic mean of x1, x2, arithmetic mean of x3, x4, and take the arithmetic mean of that. So that's the arithmetic mean of x1 plus x2 over 2, x3 plus x4 over 2. That's x1 plus x2 over 2 plus x3 plus x4 over 2 over 2, which is x1 plus x2 plus x3 plus x4 over 2, which is the arithmetic mean, and I'll put a subscript 4, x1, x2, x3, x4,
It's over 4.
over 4. So 2's can become 4's without too much trouble. So do you think this holds if I had 8 terms? Yeah. Would it be easy to show that it holds for 8 terms? We could do just the brute force like this. Can we do it by induction to say that 8 terms is really 4 terms and 4 terms? What if I had 6 terms? We would hope. So if I had 6 terms, I could look at the arithmetic mean of x1, x2, x3, arithmetic mean of x4, x5, x6. And if you want, I'll put subscripts 2 and 3 and 3 to just remind myself of how many pieces we have. And then this should just be x1 plus x2 plus x3 over 3 plus x4 plus x5 plus x6 over 3 over 2. And yes, that's x1 through x6 over 6.
Or the other way. AM3.
And then you could do it the other way around. What if we did AM3 of AM2, x1, x2, dot, dot, dot. Hopefully you can agree that this is all going to work. And no matter how I split everything, everything is going to be fine. Do we now get this trivially for the geometric stuff? Yeah, we should get it trivially for the geometric stuff by just doing a change of variables. So I'll leave that as an exercise for you. Now, according to my clock, it's not 12:35, which means we still have more material we need to do. So we've done it for the arithmetic mean, we've done it for the geometric mean. What's next? Triple mean, right? Do you think it works for the triple mean? So the triple mean of, let's say, xyz was xy plus yz plus zx over 3 to the 1/2 power, right? So how should we check a triple mean? What do we even compare it with? So we could do the triple mean of 3 things. So we could do the triple mean of, and I'll do a subscript 3 because it's 3 things, of the triple mean of 3 things, x1, y1, z1, triple mean, x2, y2, z2, triple mean, x3, y3, z3. How should I do this calculation? What century are we in? This is the 21st century. I should plug this into something like Mathematica and say expand. Can you see the nightmare beginning to come into play? Right? Oh my God, these are the 3 objects? What do we even compare this to? So we have to compare this to a 9 mean. So compare to a 9 mean. Which one? So I had to do something we didn't do in 331. All right. So Can you tell me anything about the units of this triple mean?
Cubic or cosine, quadratic or something.
Well, because we're taking square roots, they're all going to be numbers. And so at the end of the day, it's going to just be meters. I can't necessarily tell which of the 9 means because we choose the right exponent. So it's always going to collapse down.
Got all of them super.
So I don't know if you've seen Zootopia, right? You'll try everything. There's only on the order of 9 things to try. Does this equal one of them? And then you can start putting things in. Okay, so I would have, x1, y1 plus y1, z1 plus z1, x1 over 3 to the 1/2. That's my first item. Now I multiply by the second item, which is x2, y2 plus y2, z2 plus z2, x2 over 3 to the 1/2. That's the first piece, right? Then I have 2 more pieces. Then I divide this by 3. And unfortunately, it's so bad, I've run next to the margin. There you go. And so I can move it over a little bit. And now what do I have to do to this? And I have to square root the whole thing. And I need to compare this to something. Do you have?
Well, at least know that the denominator will be 9.
Mhm.
That's 3. Square root of 3 times, yeah.
Well, we're going to be careful because those 3s have factors of 1/2 hitting them.
But they're also getting multiplied together by another 3.
Yeah.
With that.
Okay, good. They be multiplied by nothing. Good, perfect. So we do know the denominator is a 9. Okay.
You're adding 9 things together.
So we're going to have mess over 9, but then the square root of 9 becomes a 3. So what do we think that this should be related to some triple mean of 9 objects, some generalized mean of 9 objects? And if so, which one? Is this the right thing to study? Would there have been something easier to look at? Well, if we're just using the arithmetic mean, geometric mean with 2 objects, we've already covered that. We've got to go up to 3 objects. The arithmetic mean and geometric mean with 3 objects is not going to be that bad. We have this. The only thing I could think of is, would it be better to look at 4 objects and things in pairs, or probably not? This might be the simplest thing we can look at.
It's like the building one, the same way, the AM is.
And so we have 9 possibilities to compare this to. 1, 2, 3, 4, 5, 6, 7. We have 1 person at home is 8, and I guess if you throw myself in this 9. So each one of us could take a mean, do the comparison, right? So, this is my question to you. Do you think that this equals some kind of, I can use maybe some kind of 9 mean of x1 ... z3? Is there going to be a choice where this works?
Yeah, because this is the function of the same variable. So we can just define it to be that.
But there's very natural choices for what these are. So for instance, if I want to look at, say, n objects maybe m, kn of x1 through xn would be, I look at all possible sums of xi1, xi2, dot, 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 xik. I take k possibilities. I have to divide it by something and then take it to a power. What power do I take it to? Only one possibility. 1 over k. If each x is in meters, the product is now in meters to the k. I want the mean to have the same units as x. So it's going to be to the 1 over kth power. What do I have to divide by? And how many things do I add?
And choose K.
And choose k. And note, if n equals 3 and k equals 2, then 3 choose 2 does equal 3. The 3 we saw before was really 3 choose 2. So these are our candidates.
Unit. The last expression we have.
So we can go back a page, or oops. I can try to bring this over to the next page. So I can bring it over here. So you want to compare that to this. Kind of terrifies me. Because in the first one, I've got products of k terms, and then I take square roots. Here, I'm going to have maybe products of 4 things with a 4th root. I'm sorry, four things with the square root, then take another square root. But what's nice is you can write a computer program and you can program in the 9 different means. And you can check and see, does anything work? And if nothing works, then there's no point in trying to prove it theoretically. What's a good set of numbers x1 through xn? Yeah, I would try 1, 2, 3, 4, 5, something like that. You have to be a little bit careful because sometimes things are not generic. If you want a generic 2 by 2 matrix, 1, 2, 3, 4, what's a generic 3 by 3 matrix? 1, 2, 3, 4, 5, 6, 7, 8, 9. What's special about this matrix? Anybody know what's special?
Does that have something to do with the determinant?
Yes. Determinant equals 0, determinant equals 0, determinant equals 0.
Okay.
And the simplest way of seeing this is notice that the first and the third, what's the arithmetic average? It's the second. Or twice the
okay.
second equals the first and the third. So this won't work when you have a 1 by 1 or a 2 by 2 matrix because you don't have 3 columns. But once you have 3 columns, the first plus the third is twice the second. So the determinant's always 0. So if I want to write down a generic n by n matrix, if I write down 1 through n squared, I've accidentally written down a matrix with the determinant 0. That's not a generic matrix. So I would definitely try the numbers 1 through n. The only thing that might worry me about that is I've got to take square roots. And so I might be worried a little bit about how well the computer can handle stuff like that. But I've got to sum things and then take square roots. It's a nightmare.
If it works, just try something else.
If it works, just try something else. Exactly. So, there's a bunch of you. I strongly encourage you as a class, make me happy. come up with some, program and just check the different possibilities and see, does anything work? When we were making the wish list, nobody had put this on, that the mean of the means is the mean. And one of the reasons is what the mean means changes. So I like the additional property that I want the mean to be monotonic, that if y is made larger, the mean shouldn't get smaller. By doing better on an exam, that shouldn't hurt your average. That actually happened to me in a math paper that I wrote with a grad student. It was rejected by the journal because we proved more than was conjectured. And the referee wrote, why would you prove more than is conjectured? I went to the editor-in-chief and said, would you like us to rewrite the paper and say, rather than noticing the following clever observation, we instead naively bound? And the editor-in-chief said, look, I get so many papers, I don't have time to deal with this. And so that was the last time I've ever submitted to that journal. I will referee for that journal only if it's a young mathematician who needs the hit for their tenure case. I will not referee any senior papers from this journal. It was absolutely ridiculous to reject because we proved too much. This is a great property. No one's ever said that before, that it should be monotonic. But this other property, that the mean of the mean should be the mean, where they're different means, is this too restrictive? The symmetric property that eliminates weighted averaging. So again, I think there's a lot here for a really good math outreach article, which can start at a low level and can get really high. I think there's a lot that can be done right now to see, is there a choice that will make everything work out? And I have deliberately not thought about this. There's only 9 candidates, so there's not that many things to try. Does anything work?
The middle one.
So one possibility is the middle one. And is there a middle one from 1 to 9? There is the 5th. And so to some extent, I would say if there has to be one to try, the 5th is a little bit reasonable, but that's going to involve 5th roots. And I don't see how I'm going to get 5th roots with stuff like this. So, to me, I would say 4 might be the natural one to try, because that's at least going to give me 4th roots, and I've got square roots of square roots. So if I, again, putting gun to my head, if I had to try something, I'd probably go with 4. I'm not optimistic that this would work, that there's any way to make this work. But I really want one of you to try this. And you can all do it together. I will provide Girl Scout cookies if you want. Okay? All right, I'll put Girl Scout cookies outside my office. All right, this is a good place to stop.